here's a free response question that shows up. It actually has to do with wheat production, but it's also showing you that, and I didn't have a question that I could easily find in the book that dealt with energy systems, but here's a wheat farm being considered as an open system, and the student in this free response question is asked to identify 2 inputs and 2 outputs of this system, talking about how much is produced per hectare, how much wheat is produced per hectare, and fertilizers get added, and it doesn't say it, but wheat gets removed, that's implied. And so the student is asked to identify 2 inputs and 2 outputs of this system. And then there's a question involving feedback loops, in this case positive feedback, and the question continues. There's a part C and a part D, and I think there's a part E. But I just wanted to show you that you could go from a topic like this and then be asked to apply it to a different system, and these are done in the free response questions at the end of each chapter. As I mentioned before, we can evaluate systems qualitatively and quantitatively. And so I just wanted to point out what that difference is and what that looks like. So for example, here in our fossil fuel non-renewable energy resource chapter, we show, if you will, a life cycle assessment of energy flow through energy resource extraction and use. But we do this very qualitatively. So in this case, there's a diagram that shows the energy resource, which is presumably a seam of coal in some bedrock, and there's extraction. This looks like it's surface mining that's removing it. And then there's transportation of the coal, and there might be processing, and then it might be brought to a combustion chamber in a coal-generating electricity station where electricity is generated, there's waste products disposed of, and the electricity is transmitted along electricity transmission lines and gets to a user. So that, for example, might be not covering all, but covering what people often call cradle to grave. I suppose the grave in this case is the disposal and transportation of the waste products, the ash, and this is the end point or the desired use. And we've tried to indicate energy losses, showing that there's pretty much energy losses everywhere along the way. And so it's really important when you're going back here and you're thinking about this system, it's really important to talk about what kind of fuel are you using and how was it obtained and what happens to the waste products. So here's a qualitative diagram. And then we also have quantitative diagrams. So this is in Chapter 2 where we're first defining systems, and we show that the overall efficiency, oftentimes people raise your hand, or if you remember how Cindy showed you how to raise your hand at the top of the dialog box, raise your hand if you do something in your class where you have your students calculate the efficiency of a conversion. In this case, it's showing coal being converted to electricity. So it looks like lots of hand raising is coming in, and so pretty much everybody, or maybe a couple of people, are having a bite to eat and their hands are busy, but certainly a lot of people are doing that. And so in this case, one part of the system is saying if you have coal sitting at your coal-fired electricity generation station, if you have whatever the energy content of that coal is, 65% of that energy content is converted to heat and is sent up the stack. 35% of the energy in that coal is converted to electricity and then transmitted to electrical transmission lines, where about 90% of what goes into the lines ends up at people's houses and at factories. And then, depending on your machine, in this case our machine is an incandescent light bulb, which is very inefficient. It's only about 5% efficient. A compact fluorescent might be 22% efficient, and an LED light bulb might be 25 or 30% efficient. So you would then multiply those different efficiencies to get the overall system efficiency. So in this case, it would be 0.35 times 0.9 times 0.05, which gives you a 1.6% efficiency. And when I show that to my students, I can't help but say and make the observation, wow, that is not very much of the energy that was contained within the coal that made it to light what we wanted, the work we wanted, light. And yet that doesn't even talk about the energy that was used to get the coal from the ground somewhere off to the left of this picture and get it to the electricity generating power plant. So that's this part of the step, which isn't even in this next diagram. So those are the kinds of things I think you can do, and you can illustrate that this is a qualitative life cycle assessment. This is a more quantitative, but only a partial life cycle assessment. So those are some things that I think are worth doing and getting people to think about. Here's another qualitative discussion that we put in our Chapter 2 in the text, and I've extracted it. And I said, let's compare the efficiencies in the home of how you could boil a pot of water. Some of us have homes where we have natural gas, or maybe we use wood, or in some parts of the world, people use animal waste to generate heat. And that heat in the form of a fire transfers to a pot where somebody cooks some soup or cooks a stew or something like that. And you could ask, what's the overall efficiency of that? Getting the energy in a flame to a pot, the transfer is about 50% efficient. Whereas if you have an electric coil on an electric stove, because the coils are flat and the pot comes in contact with the coils more effectively, it's actually a 70% efficient transfer right there. So if somebody just looked at the situation of electricity in some stovetop coils to a pot of food, they might say, well, that's a more efficient system. It's 70% efficient versus with wood or natural gas is only 50%, because as you've probably experienced, the heat of the flame goes elsewhere than just the pot. But that's not looking at the whole system. You have to look at how did you combust that energy, and how did you obtain that energy to make the flame, and how did you generate the electricity. And as we know from the last example, the electricity, if it's coal combustion, might only be on the order of 35% efficient. Times 0.9, it's even closer to 30% efficient. So those are some of the things you can do in a matter of qualitative and quantitative. One thing that I like to do is show that each one of these arrows is a conversion, either an energy conversion or a phase conversion. And I like to make the point, using the first and second laws of thermodynamics, that any time there's a conversion of energy or even a transfer of energy, you tend to get some losses. So without doing a hard assessment of each of these values, some of which are hard to obtain, you could probably say that cooking with electricity has a lower overall efficiency because it has so many more conversions. And so I always find I have an electric stovetop in my house, and where I live in Vermont, there's at least 40% or so of our electricity comes from nuclear power. And so I always think of the irony of you just want to raise the temperature of water by some tens or 100 degrees, let's say, and you sustain a nuclear reaction making steam to convert it to electricity, to convert it back to a heat product to heat up pot of food. And so these arrows indicating many, many different conversions probably suggests that the overall efficiency of this is not as good as the overall efficiency of that. How does that sound? Does anybody have anything? Maybe I went over that a little more quickly than I wanted to, so I'm going to pause for a second. If anybody has a question or they can think of something that I left out, you could raise your hand or raise your hand and then type in a question. I'm just scanning the participants. Except for some remnant hand raises from before, I think it doesn't seem like anybody has anything. That's always that tricky part about these webinars, is you can't read your audience. But at any rate, hopefully you see that I've done some different ones that are quantitative and qualitative, and in each case pointing out what is the system.